Okay students, let us see a third case and a very important case in which enthalpy change is negative and the change in entropy is also negative. An example of such chemical reaction is the most famous Haber process, in which the exothermic chemical reaction is negative. As we know that in particularly Haber process, there is 1 mole of nitrogen reacting with 3 mole of hydrogen to make 2 mole of ammonia, and the forward reaction is exothermic. At the same time, we see there is a decrease in the mole of gas. There are 4 moles of gases towards the reactant side, but only 2 moles of gases toward the product side. So there is a net change, drop in entropy. So entropy change is minus, while the enthalpy change is also minus. So if this is the case, what happens? Let's calculate on our particular formula. So I have taken some typical values, like enthalpy change is minus 200,000 joule and the change in entropy is 500. So if this is the case, we can see the Gibbs free energy is minus 150 kilojoule or minus 150,000 joule. Now if I make the entropy change to minus 1000, as you can see, it is feasible but less feasible compared to the previous case. If there is more drop in entropy, the reaction is gonna be a bit less feasible. Making it to the original value. Now if I change the enthalpy change, I make it less exothermic, like minus 100,000. So I can see it is still less feasible. Now if I change the temperature, for example I make it 200 Kelvin, so you can see it is not feasible, the value becomes 0. Now if I make it 199, so it is feasible. It means at low temperature the temperature should be lower, or the enthalpy change, this value should be higher for these particular chemical reaction to be feasible. Because you people can see there is a minus value here that is multiplying this minus value, minus minus plus. Now if this part of the equation becomes plus, this part of the equation must be more negative to make the entire answer negative. So this is a typical example of the chemical reaction like Haber process. Okay dear students, the last case where we are going to use the equation for Gibbs free energy, in which the enthalpy change is positive and the entropy change is negative. Now if this is the case, as you can see, the change in Gibbs free energy is positive. Now if I change the values, for example I make it minus 500, still it is positive. If I make it minus 100, still it is positive. If I change the temperature to 393, it is still positive. If I make it to 193, it is still positive. So whatever change I make in these two values, this is positive. If I change this value, enthalpy change, this is 100,000 joule. If I make it to 200,000 joule, the value is still positive. If I make it to 50,000, the value is positive. If I make it to 10,000, the value is still positive. So whatever the case may be, the value always comes positive if enthalpy change is positive and entropy change is negative. So we can see mathematically, like this negative multiplied by this negative, negative, the answer is going to be positive. Now this positive factor added to this positive factor, two positive values can never make a negative value. It means if this is the case, a particular chemical reaction in which enthalpy change is positive, that is endothermic, and the change in entropy is negative, so there is a decrease in the disorder, the Gibbs free energy is always positive, and that particular chemical reaction is not feasible at any temperature or under any conditions. But please remember, in senior level chemistry, uh, there are cases in which such chemical reaction also become possible, feasible. But as I told you, these chemical reactions are for only higher level of chemistry. For O and A level, so if a particular chemical reaction or physical change has positive value for the enthalpy change and negative value for entropy change, so this is not feasible at all.